Greetings. Chapter 18, Part 6. And Chapter 19, which I'm going to sort of bleed together here. So, in the previous recording, I was talking about 2-methylcyclohexanone and if you add acid or base, you'd set up an equilibrium between the enols of which there are two, and the ketone. And this is an equilibrium. Acid and base, of course, are catalysts. They speed up this through either protonation and loss of a proton, or deprotonation and then protonating the enolate. But of course, hydroxide is not strong enough to really deprotonate this very much. So we're just setting up this equilibrium. And these are alkenes. These are, in fact, enols, but they really function as alkenes here. And so, like everything you know about alkenes, the enols are more favored if they're more substituted. Of course, you can modify that with sterics and things like that, but these are relatively similar in terms of steric issues. And so you'll have a mixture of these, and you typically have about a 70-30 ratio here, right? That's a thermodynamic. Ratio here, and thermodynamics, what that really means is if you calculate their relative energies, you'd end up with a ratio that reflects those energies. Now, if you have a stronger base, and you have to have a stronger base if you want to go completely over to the enolates, and the way you do that is with LDA, which of course is lithium diisopropyl amide, which I'm going to draw with a covalent bond between nitrogen and lithium, and the pKa of a secondary amine is well above 30, and I forget exactly what your book quotes. It may be up around 38, something like that. pKa here, of course, is about 20. So that's a sort of a universal ketone pKa value. So if you go in with a slight excess, so maybe 10%, something like that, you'll have this very strong base. Do the deprotonation, and it will be irreversible, right? 10 orders of magnitude or more in terms of any kind of equilibrium. So that means going back is not really possible. So LDA is a very strong non-nucleophilic base. And so, as I said before, you can get these two enolates, right? Because I'll put the lithium in here. And and one of these, of course, if you look at this, you have two protons over here, and you've got this one proton that's very hindered. And so in LDA, this bulky base zooms in to deprotonate. You get a ratio of about 99 to 1. This is, we refer to this as the kinetic enolate, as opposed to the thermodynamic enolate. And as your textbook says, if you then go in and you add methyl iodide, you can do an SN2. Of course, this is an extraordinarily good SN2 substrate. And you can get 2,6-dimethylcyclohexanone. And of course, as I'm sure you've already thought about as soon as I said it, you can have cis and trans isomers here. They are going to be equilibratable because this has acidic protons here. And if you think about that, yes, you can put a cyclohexanone in a chair, cyclohexane, and you can put both of those methyl groups in equatorial dispositions. They would be cis because they're 1,3. So, but that is not necessarily what you get from the direct alkylation. But that's kind of discussion is really for a more advanced organic chemistry class. So, but here's what you really need to know. Here's the value put on that alkylation. And let me also give you another textbook example. Okay, so the pKa of an ester is about 25. Now, that's still plenty acidic for LDA. So you can very readily make the enolate. Now, let's see. And so now I'm going to elaborate here. And you can have E and Z. So now you have to think about where lithium is on the periodic table, if you want to think about that. Because you have oxygen, so now you have carbon and lithium. And if you throw in ethyl iodide, which is a much poorer alkylating agent than methyl iodide, just because it's a little more sterically hindered, you will alkylate very nicely, and here I believe the yield is above 90%. Right? So this is a generalization here. The ketones usually alkylate at a lower yield, esters at a higher yield. So one way to think about this is esters are lower or have a higher pKa, so their enolates are therefore more reactive, and they alkylate very easily. But let me just talk a little bit about this, because it's not talked about in your text why that's a particularly low number. There's another ketone enolate alkylation, which also is down in the 40s. But they just kind of mention that, and they say, yeah, you can do that. But this is more complicated, and I think it's worth thinking about this. And so I'm going to think about this with you here. Now, back in the day, when they really studied this, and I think this is actually kind of interesting, is they could make the enol acetates of 2-methylcyclohexanone, and they would get a mixture of the different regioisomers. And this is 20 years before, this is early 60s, so this is about 15 years before they invented LDA. And then they would go in with 2 equivalents of methyl lithium, so that attacks the ester, and then it kicks out the acetate, and then of course you get acetone, and then that alkylates again, and so you get T-butoxide in there. But the lithium, and this is not a very reactive because of the lithium alkoxide. And when they throw in methyl iodide or benzyl bromide, they would get alkylation. So as I set up here, they would get 2,6. But they would also get 2,2, and then they'd get some 2,2,6, and starting material, they'd recover ketone, 2-methylcyclohexanone, and it was, the yields were modest, and the mixtures were difficult. Now, and how is it possible that you can get something like this? Well, that's because as soon as this ketone alkylation product is formed, and it's formed slowly, so now the enolate can deprotonate, and you get your starting material, and then you get the enolate of the product, and the product alkylates to give you that, and then, you know, so this is going shuffling back and forth. It's all because the ketone enolates are alkylating slowly. And the real issue then becomes the fact that these are difficult to separate. It's not very clean. What you're really looking for is yields in the 90-ish range. And so esters are much better to work with in terms of enolate alkylation than ketones. Now, LDA wasn't invented, wasn't discovered, really invented, is the right word, until the mid-1970s, which sounds like a long time ago to you, but doesn't sound like really much longer. I graduated with my bachelor's degree in 1977, so and LDA was already known, although I was just an undergraduate and I didn't know about it until I got to graduate school. All right, so this is a little bit complicated, but I think it's relatively straightforward to understand. Now, let me tell you why this is so critical. So this is LDA, and it's 100% conversion. And I'll talk about that in part 7.